Hello, today we are going to start a new topic called as Fourier's complex integral. Before that, we'll revise what we have done in the last lecture. In the last lecture, we have started our unit 2, integral transform. So we have defined what is meant by integral transform, where f of x is equals to integral a to b f of x k in the bracket s comma x comma dx, where this term is known as kernel. I have given some examples with respect to integral transform. Laplace transform, where its kernel's value was e raised to minus sx. Then Fourier complex transform, where its kernel value is e raised to minus I sx. Then the Fourier sine transform with its kernel value sin sx, and the cosine transform with its kernel value is cos x. Then the list of formulas of Fourier integrals. These were the three list of formulas. Then we have given one proof for Fourier Integral Theorem. The statement is like f of x is equals to 1 upon pi integral 0 to infinity minus infinity to infinity f of t cos ut minus x dt du. Okay, so it's being proved by 4 steps. My first step was a naught, an, and bn values substitution. Second step was this substitution, where this term was like cos a cos b plus sin a sin b form, which was substituted as cos a minus b. Third step was I have to solve this part. My fourth step was I have to solve this part and do the further substitution. Okay, so my proof was like this, and we have proved this. And as I mentioned at the start of this lecture, that we are going to start a new topic called as Fourier's complex integrals. So Fourier's complex integrals, what does it mean? It will have the concepts of Fourier series. It will have something related to complex variables or complex numbers. If you remember, complex numbers are represented as z is equals to x plus iy. Okay, so here in this part, here what we have to prove. So in this proof, f of x is equals to 1 upon 2 pi integral minus infinity to infinity e raised to minus iux du integral minus infinity to infinity f of t e raised to minus iut dt. Okay, so let us start our proof. As we know, minus integral minus a to a f of x dx is equals to 0, as f of x is odd function. So in odd cases, we have minus infinity to infinity sin u t minus x du is equals to 0. This sign comes out to be when the functions are odd. So as a result, what we are getting it here, 1 upon 2 pi integral minus infinity to infinity f of t, again minus infinity to infinity sin t minus u du, which is equals to 0. Okay, so and I'm multiplying that term by I. So what we are getting, I upon 2 pi integral minus infinity to infinity f of t dt, again integral, that is minus infinity to infinity sin u t minus x du is equals to 0. Now on adding equation number 1 and 5, where is 5? So the fifth, we are taking it from our previous proof. This part we are taking. So what we are getting is here is f of x is equals to 1 upon 2 pi integral minus infinity to infinity again f of t cos t minus x du dt, plus this term I will write it as, so it is plus I by 2 pi integral minus infinity to infinity f of t dt. This part is remaining. It is integral minus infinity to infinity sin u t minus x du. Okay, next how I will solve. What I'll do, I'll take this term and this term together. So what I will get it is 1 upon 2 pi integral minus infinity to infinity f of t. Okay, both the terms are having dt terms, so I will take out the dt also. Now minus infinity to infinity, this term in the bracket cos t minus cos it is here cos u t minus x plus I sin u, it is t minus x into du. Okay, so whole thing it will be into du. Then what will be there in the next step is that this term we have to replace. So we will be replacing it by 1 upon 2 pi minus infinity to infinity f of t into dt. This will be minus infinity to infinity e raised to I u t minus x into du. So we are having cos u t minus u. So this is our term. If you remember, in complex numbers we have sin theta plus cos theta. In exponential form, how we were writing it as? We were writing it as e raised to I theta. So same way, this is e raised to I theta. This is exactly like a theta. Okay, so as a result, what we are getting it as f of x is equals to 1 upon 2 pi minus integral minus infinity to infinity e raised to minus I u x du into my infinity minus infinity to infinity f of t e raised to I u t into dt. Okay, so what we are getting, this thing what we were in need, we have got this. As a result, let me mark this as equation number 2. Thus what we are getting here is, thus equation 2 is called Fourier, is called what? Is called Fourier's complex integrals. Okay, so we are done with the proof. Now we'll start with one more new topic called as Fourier Transform. Before starting that topic, let's do one recap of our previous proof. As I said, it's a Fourier complex integral. It is a two-step. From my side, it's a two-step proof. This is just a basic substitutions which we have to do. So basic substitution for the Fourier complex integrals. Okay, then my step 1 is like, this is my, on adding 5 and equation number 1, we will get something like this. So this is your step 1. Then step 2 is like, so we will substitute this thing, that is cos ut minus x, that is cos ut minus x plus sin ut minus x to this value. So this is like step number 2. So from this you can say the proof for the Fourier's complex integral is a two-step proof. That is, this is your step number 1 where we will add both the equations, and step number 2 is we will substitute these complex numbers. That's it, we are getting our proof. Okay, so let's start our next proof. That is, it's not a proof actually, it's just a substitutions, and we are going to understand what the Fourier transform is. What exactly the Fourier transform is. So we will write this equation number 2, what we have proved is. So now from equation, so we will refer equation from equation 2, f of x is equals to 1 upon 2 pi integral minus infinity to infinity e raised to minus iux du integral minus infinity to infinity f of t e raised to iut dt. So what it will give me, what I will do, instead of u I will substitute this thing as s. So it is 1 upon 2 pi minus infinity to infinity e raised to minus I. I said instead of u I'll substitute value as s x. This will be ds. Again integral minus infinity to infinity f of t and this will be e raised to ist dt. So as I told you, u is equals to s. Okay, now let me mark this as equation number 1 for this one. Okay, now substituting this integral minus infinity to infinity f of t e raised to ist dt is equals to fs in equation 1. So we get, that is f of x is equals to 1 upon 2 pi integral minus infinity to infinity e raised to minus I sx into f of x into f of s into ds. Okay, into ds. So let me mark this as equation number 3. So what I have done, I have taken this equation number 2 where same as it is, this whole part, instead of u I have substituted s. Then what I have taken, this part I have denoted as f of s and I have marked this as equation number 2 also, and then substituting this value in equation 1. So we are getting something like this. So in these equations, so thus in equation 2 f of s is called, it is called as Fourier Transform of f of x. Okay, so that is a Fourier transform. And then in equation 3 f of x is called inverse Fourier transform of f of s. Okay, so for reason of symmetry, we multiply both f of x and capital F of s by square root of 1 upon 2 pi. Instead of having factor 1 upon 2 pi in only one function, thus we obtain the definition of Fourier transform as f of s is equals to 1 upon square root of 2 pi integral minus infinity to infinity f of t e raised to I s t into dt, and f of x is equals to 1 upon square root of 2 pi integral minus infinity to infinity f of s e raised to ds. Okay, hence proved what we have to prove. I hope it's clear what we have done in today's lecture. We have started with Fourier integrals, Fourier complex integrals, and then I have given you some definitions for Fourier transform. Okay, thanks for watching.